Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is the beginning of Chapter 9. So, Chapter 9, which is about infinite series. And before we talk about infinite series overall, in 9.1, let's talk about sequences. So, let's start with a definition. A sequence is a function whose domain is the set of positive integers. It is usually represented as something like a sub n or the set of a sub n. Alright. In general, I'll probably be sticking to this notation. Most just a sub n without the curly brackets, but both are really mean the same thing. The terms of a sequence well, we could say we have a sub 1 and a sub 2 or a sub 3, right? Because in here, these subscripts, the 1, 2, 3, 4, those are our domain, right? Positive integers. So that's what we would plug it into them. And so on and so forth. So there's the first term, second term, third term, fourth term, so on and so forth. And in general, when we write a sub n, we really mean the nth term of the sequence. Notice here that here I have two ways to describe what a sub n is, the nth term, but also just the general representation. Well, that's because a sub n, the nth term, is really just talking about, well, what will happen if I plug in any n, all right? So just like the generic idea behind it. So for example, let's find the first four terms. Let's do five. The first five terms of each sequence. All right. So here we go. Let's say that we have the sequence a sub n is equal to 3 plus negative 1 to the n. All right. So, well, we want to figure out what the first five terms are. So, well, what's a sub 1? A sub 1, plug in 1. Negative 1 to the 1, that's negative 1. 3 plus negative 1 is 2. A sub 2, plug in 2. Negative 1 to the second, positive 1. 3 plus 1, 4. A sub 3, plug in 3. Negative 1 to the third, negative 1. 3 plus negative 1, 2. A sub 4, negative 1 to the fourth, positive 1. 3 plus 1 is 4. So on and so forth, right? So we can clearly see with the pattern 2, 4, 2, 4. So a sub 5 would be 2, right? And we can verify that by plugging in 5. All right. So those are the first five terms of the sequence. Let's see another one. Let's say that I had b sub n is equal to cosine of n pi over 2. All right. So let's figure out what happens here with this one. B sub n, and here notice I'm using just the letter B instead of A. That's really just saying, well, it's just a different name sequence, right? But it's still the same notation of a letter with a subscript n. So in here, well, let's plug in 1. Let's figure out what B sub 1 is, right? Because we want the first five terms. So that's cosine of 1 times pi over 2. So 1 times pi over 2 is just pi over 2. Cosine of pi over 2 is 0. B sub 2, plug in 2. 2 times pi over 2, so the 2's cancel out, so I just really have cosine of pi. Cosine of pi is negative 1. B sub 3, so cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0. B sub 4, plug in 4. So I have cosine of 4 pi over 2. 4 pi over 2 is the same thing as saying 2 pi. So cosine of 2 pi is the same thing as saying cosine of 0, which is 0. But no, it's not 0. Cosine of 0 is 1. There we go. B sub 5, plug in 5. Cosine of 5 pi over 2. That's equivalent to saying cosine of pi over 2, right? Cosine of 5 pi over 2 is the same thing as saying cosine of 5 pi over 2 minus 2 pi, right? Because that's removing a full rotation, right? Think about the unit circle, giving us here just cosine of pi over 2, which is 0. All right. So let's see the next one. Let's say that we have the sequence C sub n is negative 1 to the n plus 1 over 2 over n. Let's see what we get here. All right. So C sub 1, plug in 1. 1 plus 1 is 2. Negative 1 to the second is positive 1. 2 over 1 is 2, so overall I end up with just 2. Plug in C sub 2. 2 plus 1 is 3. Negative 1 to the third is negative 1, so I end up with negative. Plug in 2 over here. 2 over 2 is 1, so negative 1. C sub 3. Plug in 3. 3 plus 1 is 4. Negative 1 to the fourth is positive 1. 2 over 3 is 2/3, so I end up with positive 2/3. C sub 4. Plug in 4. 4 plus 1 is 5. Negative 1 to the 5 is negative 1. 2 over 4 is 1/2. C sub 5. Plug in 5. 5 plus 1 is 6. Negative 1 to the 6 is positive 1. 2 over 5 is just 2/5, so we end up with positive 2/5. Right? So on and so forth. Right? Now these are just some total types of sequences here. Alright? And again, sequences are functions where we're only plugging in the whole numbers. So for example, if I had, so I want to show you the difference between a sequence and a function. Right? So if I had f of x is equal to x squared versus a sub n is equal to n squared. These are very similar, but not the same. So in here, f of x equals x squared. That we already know looks like this parabola, right? But if I have a sub n equals n squared, well, that would be this, right? At 1, we're at 1. At 2, we're at 4. At 3, we're at 9. Just like that, just all those dots, all right? So on and so forth with that. Whereas over here, we actually formed the parabola because we were plugging in all the points in between, right? Like 1/2 and 1/4. We can't plug those into here, all right? Similarly, if I had something like f of x is equal to the square root of x versus a sub n is equal to the square root of n, well, in here, we already know what this one looks like. It looks like this, right? But now for a sub n, let's see what that one looks like. That would look like this. So plug in 1, I end up with 1. Plug in 2, I end up with radical 2. Plug in 3, I end up with radical 3. Maybe I'll make that a little bit better. So on and so forth. Right? So, that should look a little bit better. Let me fix that a little bit. It should look a little bit more curved. So it would be like all these points, right? Without connecting them, it's just all those points. All right. So now, those are some of the functions. Let me see some of the sequences that we did there. Now, there are other types of sequences there's something called recursively defined sequences. I'm not going to spend too much time on them. I just want you to be exposed to their existence. So for example, I can have that d sub 1 is equal to 36 and d sub n plus 1 is equal to d sub n minus 6. Alright, so this is recursively defined. What I mean by recursively defined is that we define the first term. We say what the first term is. And then we say every term, well, in this case I've defined what the first term is. You can define it to be more than one. But in here we define just the very first term and we said, well, every term after that is defined this way. So in other words, what would that mean? Well, that would mean that d sub 2 would be, by this definition, d sub 1 minus 6. In other words, 30, right? Because d sub 1 is 36. D sub 3. D sub 3 would be d sub 2 minus 6, which in this case would be 24. So on and so forth. D sub 4 would be 18, right? And I'll write y is d sub 3 minus 6, so 18. D sub 5 would be d sub 4 minus 6, so it would be 12. All right. So that's a recursively defined sequence. Let's look at another one. I said that we don't necessarily need to have just the first term. We can define it using multiple terms. So let's say that I have a sub 1 is equal to 1. A sub 2 is also equal to 1. And then I'm going to define a sub n plus 2 to be equal to a sub n plus 1 plus a sub n. So what does that mean? Let's see. So we're saying these are the first two terms. Then we're saying the third term and beyond are defined this way. So a sub 3 would be a sub 2 plus a sub 1. In other words, it is 2. Right? Because it's 1 plus 1. A sub 4, that would be a sub 3 plus a sub 2. In this case, well, a sub 3 is 2, a sub 2 is 1, so we end up with 3. A sub 5, that's going to be a sub 4 plus a sub 3, and that's an A. And what does that give us? Well, a sub 4 was 3, a sub 3 was 2, so it's 5. And we can continue, right? Think about this. All that's really happening here is we're adding the previous two terms. So if I have a sub 6, that would be 5 plus 3, which is 8. A sub 7, that would be 8 plus 5, which is 13. A sub 8, that would be 8 plus 13, which is 21. All right. This should look familiar. This sequence should look familiar. This is called the Fibonacci sequence. Fibonacci, I think. Yeah, it has one N. Okay. The Fibonacci sequence. All right. So the Fibonacci sequence is something that's very famous, and it's something you should be familiar with by now. But again, this is a recursively defined sequence, and I'm not gonna spend too much on that. Now, let's talk about something called the limit of a sequence. So theorem. Limit of a sequence. So if I have, so let's say, let L be a real number. Let F be a function of a real variable such that the limit as x goes to infinity of f of x is equal to L. If a sub n is a sequence such that f of n is equal to a sub n, in other words, the function and the sequence agree at all the whole numbers, right? When you plug it in whole numbers. So for every positive integer, then the limit as n goes to infinity of a sub n is also equal to L. Alright, so here what are we saying? When we did limits overall, we did them with functions, right? So let's say that I had, for example, this function f of x, something like this, right? And in here, we know that we have this horizontal asymptote of 0, essentially, right? When we're talking about a sequence, however, we're only talking about when we plug in the whole numbers. So, for example, here, and here, and here. Right here in yellow, I'm drawing the sequence. So this is the sequence. So what we're saying here is, well, if the sequence and the function agree at every time you plug in a whole number, right, then they're going to have the same limit because they're behaving the same way overall, right? That's what this theorem is saying. All right, so let's see how we can apply this. Let's find some limits of sequences. Find the limit of a sub n defined as 1 plus 1 over n to the n. All right. So here we go. Let's see. What are we going to do? Well, the very first thing I'm going to do here is, well, I'm going to come up with a function f of x. I'm going to say f of x is equal to 1 plus 1 over x to the x. So what we really want to do is, we want to take the limit as x goes to infinity of this function. So let's see, what does that give us? The limit as x goes to infinity of 1 plus 1 over x to the x. If I let x go to infinity, well, what does this give me? This piece right there, 1 over x, that goes to 0, so I end up with just 1 to the infinity. We don't like that. We don't like that. We don't like 1 to the infinity, right? That's an indeterminate form. So we know ways to work around that, right? And perhaps I should say here, well, note that f of n is equal to a sub n, right? If I just plug in n, all the whole numbers, that's the same thing as the sequence. Okay, now, well, how do we deal with this? If you recall from the section regarding L'Hopital's rule, we said that this we can rewrite as y is equal to the limit as x goes to infinity of 1 plus 1 over x to the x. And then we take ln of both sides, so this gives me now that ln of y is equal to x times, the limit as x goes to infinity of x times 1 plus, oops, I forgot the ln, of x times ln of 1 plus 1 over x, right? I took ln of both sides, rules of exponents, brought the exponent to the front of the log. Now, at that point, well, I still can't use this. I still can't plug in infinity, because if I plug in infinity, well, what do I get? This part right here goes to infinity, and then this part right here, well, 1 over infinity, that goes to 0. 1 plus 0 is 1. Ln of 1 is 0. So I have infinity times 0. We don't like that. So what we can do is, well, we're going to have to manipulate this somehow. And how? How are we going to manipulate it? Well, let's see. In here, let's look at some algebra rules here. If I have a number and I'm dividing it by another number, that's the same thing as saying a number times the reciprocal of that number. Another way of thinking about this is, well, let's just do it that way. A number divided by a number is a number multiplied by its reciprocal, right? That's kind of like how we define divided by fractions. Well, another way of thinking about this multiplication is that the multiplication, I can start with a multiplication and turn it into a division by dividing by the reciprocal, right? The reciprocal of 1 over b is b. So I'm just taking a and dividing it by b. So, all right, so now, how does this apply here? Well, what I'm going to do here is, well, this ln of y is still there. Ln of y is equal to, in here, we have the limit as x goes to infinity. This x, I'm going to write it as dividing by 1 over x, right? Because dividing by 1 over x is the same as multiplying by the reciprocal. The reciprocal of 1 over x is just x. So these two statements are the same, right? And now that we have that, well, we still can't let x go to infinity because the top goes to 0, but the bottom also goes to 0. However, now we can apply something called L'Hopital's rule, right? And as we apply L'Hopital's rule, well, what did it say? It said take the derivative of the top. So I have 1 over 1 plus 1 over x times negative 1 over x squared. And also take the derivative of the bottom, negative 1 over x squared. At that point, we say, well, I have a negative 1 over x squared on top and on bottom, so they cancel each other out. As x goes to infinity, this 1 over x goes to 0. So overall here, I end up with that ln of y is equal to, well, just 1, right? Because everything else cancels out. And if ln of y is equal to 1, that tells us that y is equal to e to the 1, in other words, e. So what we found here is that the limit as x goes to infinity of 1 plus 1 over x to the x, that's equal to e. But that's not the problem that we were asking about, right? What we were asking about was the limit as n goes to infinity of 1 plus 1 over n to the n. And then by our definition from before, this has to also be equal to e because the function itself went to e. Alright? So essentially what I'm getting at here is to find the limit of a sequence, turn it into a function, and then do all the rules of limits that you're already used to from limits in Calc 1, right? So let's go through some properties here that are all properties that work in the same way with functions. But in here, I'm just going to define them for sequences. Properties of limits of sequences. So if I let the limit as n goes to infinity of a sub n equals L, and the limit as n goes to infinity of b sub n equals k. Alright, so if I let those two things be true, well, we have that the limit as n goes to infinity of a sub n plus or minus b sub n would be L plus or minus k. Alright, so the sum or difference of two sequences, if I take their limit, you can just add or subtract the limits themselves. Alright, similarly, we have the limit as n goes to infinity of a constant times a sequence. Right? If I have a constant times a sequence, that's just the constant times the limit of the sequence. Alright, and in here, c can be any real number. If I have the limit as n goes to infinity of a product of sequences, well, I can just multiply the products themselves, the limits themselves. And if I had the limit as n goes to infinity of a quotient of a sequence, well, that would just be the quotient of the limits themselves, provided that b sub n is not equal to 0 and k is also not equal to 0. Alright. So all these rules for limits, they're all the same exact thing as what we had um, for functions, right? So all these limits for sequences are the same as the limits for functions. So let's go through some limits. So now, example G. Determine convergence or divergence of the sequence. All right. And just as a reminder, convergence meant that it actually approached a specific value. Divergence meant that it did not approach a specific value. All right. And there's two ways that something can diverge. It can go to one of the infinities. In other words, it can go to positive infinity or negative infinity, or it can oscillate. All right. So, for example, if I had, we'll go through an example right now, actually. So G, if I had a sub n is equal to 9 plus 2 times negative 1 to the n. Well, let's see what would happen here. If I start putting out all the terms, right? So a sub 1, negative 1 to the 1, that's 1. 2 times, excuse me, that's negative 1. 2 times negative 1 is negative 2. 9 plus negative 2 is 7. A sub 2, negative 1 squared is positive 1. 1 times 2 is 2. 2 plus 9 is 11. A sub 3, I'll skip the work, it's 7. A sub 4, 11. A sub 5, 7. So in here, then obviously going on forever, right? So in here, what do we see? Well, we see that our sequence is alternating, our sequence is alternating between just two values, 7 and 11, right? So in other words, what am I saying here? Here's 7, here's 11, here's 7, here's 11, here's 7, here's 11. So what would the limit of this be as n goes to infinity? Well, it turns out that it doesn't actually approach anything because it's essentially here oscillating, right? It's going up and down between those two variables, between those two values. So this is oscillating. So in here, when I say the limit as n goes to infinity of a sub n, it does not exist because it oscillates. All right, cool. Next one. So that was G. H. Let's say that b sub n is equal to n over 1 minus 2n. So what we really need here is the limit as n goes to infinity of n over 1 minus 2n. Alright, as written, there's not much we can do there, but what we can do here is we can multiply by 1, and that 1 is 1 over n over 1 over n. Alright, and now what can we say? Well, this limit becomes now the limit as n goes to infinity of 1 over 1 over n minus 2. As n goes to infinity, 1 over n goes to 0, so I end up here with negative 1/2. Alright, notice here I'm just treating this as if it was overall just a function. And I mean, it is a function, but it's just a function of the positive integers versus the function of the real numbers. Alright, so, and in here it was fine that I did it this way because we didn't really need to change to the variable x because we weren't applying any crazy rule for limits at least. But let's look at this next example. So I have n squared over 2 to the n minus 1. Now in here, let's see what happens when I take the limit. If I take the limit as n goes to infinity of n squared over 2 to the n minus 1, well, I end up with infinity over infinity, right? N squared, so infinity squared, infinity. 2 to the infinity, infinity, minus 1, infinity. That's indeterminate. So we know that a way of going around indeterminate form, but we must first change this to the variable x, right? So by that I mean L'Hopital's rule, which is what we're going to want to use here. L'Hopital's rule is only defined for functions. So I have x squared over 2 to the x minus 1. So it's only defined for functions of real variables. So what we want to do here is we want to find that limit. So we're going to say the limit as x goes to infinity of x squared over 2 to the x minus 1. Using L'Hopital's rule, I end up with the limit as x goes to infinity of 2x over 2 to the x times ln of 2. If I let x go to infinity here, 2 times infinity, infinity. 2 to the infinity, infinity times ln of 2, still infinity. So we don't like that. So we're going to take L'Hopital's rule again, because we had indeterminate form, right? Infinity over infinity. So if I say the limit as x goes to infinity of the derivative of the top, 2, times the derivative of the bottom, 2 to the x times ln of 2 times ln of 2. Alright, and now here we have the top is just 2, the bottom is going to infinity, so overall it goes to 0. So what that tells me now, so that limit for the variables, for the real variable, it went to 0. So that tells me now that the limit for the sequence of n squared over 2 to the n minus 1 is also 0. Alright. Oh, by the way, I just realized I haven't been following the instructions. It said determine convergence or divergence. We really should say what happens here. And here, since the limit does not exist, it is divergent. Right? It is divergent. And this next one, the limit went to a specific value, so it's convergent. And the limit went to a specific value, 0, so it is convergent. Alright, and again, convergent means it went to a specific value, divergent means it did not go to a specific value. It is very common for people to think that divergent means it goes to positive infinity or negative infinity. And while it's true that going to positive infinity or negative infinity does mean that it's divergent, it is not necessarily true to say that that's the only way that something could be divergent. Alright, recall the oscillating case. So if it oscillates, it's divergent, right? Okay, now let's talk about something called the squeeze theorem. Now, the squeeze theorem, we have you should have seen that in Calc 1, but here we're going to do the squeeze theorem for sequences. Alright, and this is what the squeeze theorem for sequences says. It says if the limit as n goes to infinity of a sub n is equal to L, and the limit as n goes to infinity of b sub n is also equal to n, and there exists an integer n such that a sub n is less than or equal to c sub n is less than or equal to b sub n for all n greater than capital N, then the limit as n goes to infinity of c sub n is equal to L. Alright, so what are we saying here? It says, let's say that we have two sequences, a sub n and b sub n, and they're going to, they both have the same limit. Alright, and let's say that we have a third sequence, c sub n, such that after some value, c sub n is in between both a sub n and b sub n. So this sequence is in between both of these two, which we knew what the limit of them were. So if after that value, if after some value n, the entire sequence of c sub n is strictly between these two sequences, then the limit of this sequence c sub n is L, because the limit of the other sequences was also L. Alright, so that's the squeeze theorem for sequences. it's essentially saying the same exact thing as a squeeze theorem for functions, except that we're adding this fact that x must be going to, n must be going to infinity. Now, let's see how to apply this. Actually, let's see a visual first. So let's say that I had some function like this, right? Let's give me some sequence like this, and I'll do it in blue. I'm gonna call a sub n in blue. So it can be doing a whole bunch of stuff. It can be doing something like this, like that, like that, like that, like that. But then after a certain amount, it just gets closer and closer to this horizontal line here. All right. And let's say we also had this other one over here, b sub n, which I'll do in yellow, which again can be doing a whole bunch of things. Maybe it starts doing this. And then we have a third one there, c sub n, which again, it can be doing a whole bunch of stuff in the middle or at the beginning. In fact, it can go, well, let's actually make it, I'm gonna exaggerate it. Notice that it started by going up, then very far down, then really far up, then really far down, then this value up here. And then after a certain point here, these are capital N, after here, the purple stays within the yellow and the blue, right? So we can say that all three of them, so this is at the height of L, all three of them would have that limit L. All right. All right, so that's visually what's going on there. So let's do an example here that would be helpful. Let's say I said let c sub n be equal to -1 to the n over n factorial. All right. Now let's see here. This is alternating, right? Because of this negative value, -1 to the n. Our sign is going to be alternating, but the idea here is we want to figure out what's really happening here. Well, since this is alternating, well, we know for sure that -1 to the n over n factorial is going to be strictly between 1 over n factorial and -1 over n factorial. That's not really that helpful because of the factorial. What do we do there? Well, let's think about this. N factorial overall, how was that defined? That was n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1, right? So this is a huge number here. And if I'm going to take n to go to infinity here, right, so the limit as n goes to infinity of n factorial, well, that's going to be infinity because I'm just multiplying a huge number times all the natural numbers below it, right? If I start with a million here, for example, I'm doing a million times 999,999 times 999,998, so on and so forth. So that's going to end up going really quickly to infinity, right? So in here, if I take, so this actually tells me that if I take the limit as n goes to infinity of 1 over n factorial, well, that, if I have n factorial on the bottom, we know that the limit as n factorial as n goes to infinity of n factorial is infinity. So down here, this is going to infinity. So I have 1 over infinity. So I have 0. 1 over infinity is 0, right? So what does that tell me? Well, let's look at this thing again. Down here. If I take the limit of this, well, let's split this up a little bit. if I take the limit as n goes to infinity of each of these, but what do I have? On the left side I have 0, and I have 0 is less than or equal to the limit as n goes to infinity of negative 1 to the n over n factorial, and this side is also 0. So what does that tell me? That tells me that by the squeeze theorem, the limit as n goes to infinity of negative 1 to the n over n factorial is also equal to 0. All right. Now in here, this, why did we need to do the squeeze theorem in this one? The reason was really because of that negative 1 to the n. That negative 1 to the n in general makes things alternate, right? So essentially, it's going to positive values and negative values and positive values and negative values, so on and so forth, depending on what the value of n is. So it's alternating it, making it essentially oscillate. All right, if we have our x-axis, we're going from from negatives to positives to negatives to positives. So it kind of looks like it's oscillating, but the question is it actually oscillating in a way that it's getting smaller or getting closer to a specific value, or just oscillating? And in this specific scenario, it was oscillating in a way that it was actually approaching a limit. All right. Now, next theorem I'm going to use. So in here for this squeeze theorem, this essentially will just allow us to define what 1 over n factorial was going to. All right. Now let's see. Let's do another theorem here. And this one's called the absolute value theorem. And this is what it says. It says if the limit as n goes to infinity of a sub n, of the absolute value of a sub n, is equal to 0, then the limit as n goes to infinity of a sub n is equal to 0. All right, so this only works if it's going to 0. So in here, this is telling us if we have a sequence and we just work with the absolute value, it's good enough. If it's going to 0, then it's good enough to just say what the sequence overall is doing. All right, but it specifically is if it's going to 0. So let's see. If I had a sub n is equal to negative 1 to the n times 5 to the n over n factorial. All right. So in here, what can we do? Well, what we can do is we can take the limit as n goes to infinity of the absolute value of a sub n. In this case, that would be the limit as n goes to infinity of the absolute value of negative 1 to the n times 5 to the n over n factorial, which would give us the limit as n goes to infinity of, well, the absolute value of negative 1 to the n is just positive 1. So I just have 5 to the n over n factorial. Notice I got rid of the absolute values because, well, 5 to a power, it doesn't matter what the power is. That 5 is, that numerator is always going to be positive. N factorial, always positive because it's just defined for positive values. So this is all positive. Now, what does this go to? All right, let's consider that sequence. So if I have 5 to the 1, so I have 5 to the 1 over 1 factorial, right? That's the first term. 1 factorial is just 1. Then I have 5 squared, so 25 over 2 factorial, which is just 2. 25 cubed, 5 cubed, so 125 over 3 factorial. And then 625 over, 3 factorial, that's 24. No, that's not true. 3 factorial is 6. Sorry. 3 times 2 times 1. Then this was 5 to the 4th. On the bottom, I'm going to have 4 factorial, which is 24. Then, well, hold on. Let's look at this. I'm running out of space. I'm taking more space than I expected. But let's think about this. If I start just multiplying a whole bunch of 5s, right? 5 times 5 times 5 times 5 times 5 times 5 times 5, so on and so forth forever. Versus on the bottom, I'm multiplying factorial. So 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. Well, what's going to be bigger? Multiplying just 5s or multiplying numbers that get bigger and bigger as we go along, right? Well, it turns out that when you're multiplying just 5s, it's not growing as fast as when you're multiplying by numbers that are getting bigger, right? Because, I mean, after here, look at this. The top I multiply by 5, but the bottom by 6. That's already multiplying by a bigger number. Multiply by 5 again on the top, but now I'm multiplying by 7 on the bottom. So on and so forth. Over here, multiplying by 5 on top, but I'm multiplying by 10 on bottom. So that's even bigger. That's twice as much on bottom that I'm multiplying. Right? So in here, this should give you a feeling for what's actually going to happen here. So let's see. So what we're going to get now is that the limit as n goes to infinity of 5 to the n over n factorial, that's going to go to 0. All right? That's going to 0. And again, it's because on top, we just keep multiplying by 5. But on bottom, we're multiplying by bigger numbers at every point, right? As n goes to infinity, right? N is going to infinity. As n goes to infinity, at one point on the denominator, we're going to multiply by 1,000,000. But on the top, we're still going to be multiplying by 5. So that should give you an idea that the bottom is getting bigger much faster. In fact, factorials, so maybe I'll make a note here. In fact, so note, the limit as n goes to infinity of, well, yeah, that's fine, of a to the n, right, over n factorial, it's equal to 0. So in here what I'm saying is, if I have an exponential and I'm dividing it by a factorial, and I'm taking the limit as n goes to infinity, well, overall, this is going to go to 0, because again, the denominator is getting bigger much faster than the numerator. All right, now let's shift gears a little bit. So find the sequence whose first 5 terms are given. So let's say that I have this sequence: 2, 4 over 3, 8 over 5, 16 over 7, 32 over 9, so on and so forth. 1, 2, 3, 4, 5, yeah. So what we want to do here is we're going to figure out, well, what is this sequence? We've got a whole bunch of terms. What is this sequence? Well, let's see. Let's look for patterns here. Let's look for the numerator. What do we see about the numerator? Well, we started with 2, then 4, then 8, then 16, then 32. What's going on there? We're doubling. We're doubling every single step. So in other words, we just keep multiplying by 2 on the numerator. Oh, hiccups, no. So on the numerator, we just have powers of 2, right? 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So in the numerator, so our sequence in the numerator, we're going to have 2 to the n. Now, let's look at the denominator. The denominator here, that's an invisible one, right? So let's look at the denominator. 1, 3, 5, 7, 9. Well, they're going up by 2. But more importantly, they're odd values. They're going up by 2 and they're odd numbers. So if I need to start off at 1, well, how do I define an odd number? Well, normally we would say a number can be defined as 2 to the n plus 1 if I start at n equals 0. Maybe I'll write it in here, starting with n equals 0, or 2 to the n minus 1 when we're starting with n equals 1. Alright, so in here, this is the, if I'm going to start with n equals 1, I have to rewrite the denominator here as 2n minus 1. Alright, because again, let's plug in the value, the natural numbers, right? 1, 2 times 1 is 2, minus 1 is 1. Plug in 2, 2 times 2 is 4, minus 1 is 3. Plug in 3, 2 times 3 is 6, minus 1 is 5, so on and so forth. So we know that this right here actually is the sequence described by those 5 terms. And if we really wanted to here, well, let's figure out whether it converge or diverge. So converge or diverge. So if I take the limit as n goes to infinity of 2 to the n over 2n minus 1, well, that's going to be the same thing as saying the limit as x goes to infinity of 2 to the x over 2x minus 1. And, excuse me, 2 to the x, not 2 to the n, 2 to the x. And now I can use L'Hopital's rule, right? Because as written, I get infinity over infinity. So if I use L'Hopital's rule, I end up with the limit as x goes to infinity of 2 to the x ln of 2 over just 2. And at this point, what do we see? Well, as x goes to infinity, this entire thing just goes to infinity, right? 2 to the infinity is infinity times ln of 2, still infinity, divided by 2, infinity still. Okay, so we get infinity. So because we got that it went to infinity, that does not converge. Therefore, we'll say it is divergent. All right. Let's look at another one. Let's look at another one. So that was L. M. Let's say that I had the following sequence: negative 1/5, comma, 2 9s, negative 4 13s, 8 17s, so on and so forth. 1 2 3 4 5. Okay. So let's see what we can do here. The numerator, the numerator is still. Oh, you know what? Let's no, that's fine. We'll leave it as that. The numerator is still powers of 2, right? Starting with 1, doubled 2, doubled 3, excuse me, doubled 4, doubled 8, doubled 16. But we also see that we have the sign is alternating, negative, positive, negative, positive, negative. So we have an alternating value there. So all right, so let's see. Whenever we have an alternating thing like that, well, it's one at a time. We're gonna say we have negative 1 to the n. Right? Now we need to start at 1. Remember, we need to start at 1. So how do we end up with? We need to start with n equals 1. Sorry. So what can we do there? So n has to start at 1. How do I get these powers up here? Well, I'm going to tell you this is 2 to the n minus 1. How? Plug in 1. 1 minus 1, 0. 2 to the 0, 1. Plug in 2. 2 minus 1, 1. 2 to the 1, 2. Plug in 3. 3 minus 1, 2. 2 to the 2, 4. Plug in 4. 4 minus 1, 3. 2 to the 3, 8. Plug in 5. 5 minus 1, 4. 2 to the 4th, 16. So we have the negative 1 here to the n for the alternating. We have 2 to the n minus 1 for the powers of 2 on top. And on the bottom, let's see. How can we start? We start 5, and then 9, then 13, then 17, then 21. So what we have there is we're adding 4 each time. We're adding 4 each time. So how can we think about that? Well, let's see. In here, since we're adding 4 each time, really, well, let's see. Let's look at that 5. 5 is the same thing as saying 4 times 1 plus 1. 9 is the same thing as adding 4 to that, right? But if I had 4 times 1 plus 1 and I add 4, that's the same thing as saying 4 times 2 plus 1. If I have 13, that's the same thing as adding 4 here. So if I have 4 times 2 plus 1, and then I add 4, I have 4 times 3 plus 1. Hopefully you see the pattern that's going on here, because in the bottom what we're going to have is just 4n plus 1, right? And here, let's see, this is for the fifth term, right? Let's see what happens on the fifth term. 4 times 5, 20, plus 1, 21. Nice. 5 minus 1, 4, 2 to the fourth, 16. Nice. Negative 1 to the fifth, negative 1. There's the negative. Nice. So that means we actually have the correct sequence here. And I'll leave it at that. All right. There are other properties of sequences. All right. So let's discuss some of those properties a little bit. And I won't necessarily go into too much detail into them, but I do want you to know that these things exist. So, definition. Monotonic sequences. So really I'm just going to be defining some terms here. So monotonic sequences. A sequence is monotonic when its terms are non-decreasing or non-increasing. What do we mean by that? Well, let's look at non-decreasing. Non-decreasing would be that every term is getting bigger, or at least staying at the same height. So for example, if I had a sequence like, let's say a sub n is equal to, I don't know, let's do simple, 3 to the n. This is a monotonic sequence because we start at 3, which is less than or equal to 9, which is less than or equal to 27, which is less than or equal to 81. All right, so on and so forth. So in here, all the terms are getting bigger or staying at the same height as before. You know, I can also have something that looks like this. 5 less than or equal to 6, less than or equal to 6, less than or equal to 7, less than or equal to 9, less than or equal to 9, less than or equal to 10. That would also be, if I had that sequence, 5, 6, 6, 7, 9, 9, 10, that would also be non-decreasing, because even though in here it didn't get bigger, going from 6 to 6, it did not decrease. It stayed at least at that height. So that would be non-decreasing. Now, let's look at non-increasing. Well, it's the same exact idea, just going the other way, right? So a sub 1 is going to be bigger or greater than or equal to a sub 2, which is greater than or equal to a sub 3, so on and so forth. All right, so we can have something like, I don't know, let's do a sub n being 1 over n, right? So 1 over 1, 1, that's bigger than 1/2, which is bigger than 1/3, which is bigger than 1/4, which is bigger than 1/5, so on and so forth, right? So that would be a non-increasing function, excuse me, a non-increasing sequence. Another way to look at a non-increasing sequence would be, so something like, if I have the following terms, 9, which is greater than or equal to 9, which is greater than or equal to 7, which is greater than or equal to 5, which is greater than or equal to 4, which is greater than or equal to 4, which is greater than or equal to 2, so on and so forth. All right. The idea here is that even though, for example, here from 9 to 9, it didn't go smaller, it also did not go bigger. Similarly here from 4 to 4, it didn't get smaller, but it also did not increase. So it's a non-increasing function versus saying it's a non-increasing sequence versus saying a decreasing sequence. All right, so that's just some terminology there. There's also bounded sequences. So let's look at a definition for a bounded sequence. And in here, well, let's get a definition. That's not what I meant to write. All right. So a sequence A sub n is bounded above when there is a real number m such that A sub n is less than or equal to m for all n. The number m is said to be an upper bound, or is called an upper bound of the sequence A sub n. Alright, next definition. And I'll give actually in fact I already give a sequence like that, right? And here, the sequence is bounded by 1 above. In here, this sequence is bounded by 9 above. Right now was the biggest possible value. So that's what we mean by bounded above. 2. A sequence A sub n is bounded below when there is a real number n such that A sub n is greater than or equal to n for all n. What? For A sub n is greater than or equal to n for all n. Period. The number n is called a lower bound of A sub n. Alright. So same exact idea, but now we're bounded below. So for example, over here, in this one, it was bounded below by 3. This one is bounded below by 5. Alright? So that's for bounded below. 3. A sequence is bounded when it is bounded below and above. Below and above. So for example, this one right here, it's bounded above by 1. Right? 1 is the biggest possible value that we get there. It's bounded, so that's bounded above. It's bounded below by 0 because, well, no matter what I plug in here, it's never going to get to be smaller than 0, right? Even when I get to 1,000,000, 1 over 1,000,000 is still bigger than 0, all right? So this is bounded from below and from above, which we would say there that that sequence is bounded, all right? So in here, A sub n equals 1 over n is an example of a bounded sequence. Another one. So let's see, b sub n would be cosine of pi n. Alright. Let's do pi over 2n. That's fine. Cosine of pi over 2n. That's also bounded because if you look at what that is, well, it is this. It's bounded below and above. We're not going above 1. We're not going below -1. So this is a bounded sequence. Alright. And there's many types of examples for these. But as far as this class goes, I just want you to understand in general that these things exist. That's why, well, these definitions are things that could be ways to describe a sequence. All right, that is the end of 9.1.
Wasn't that fun?
If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.